Okay, 13.1, vector functions and space curves. Vector function and space curve. A vector valued function is a function whose domain is a set of real numbers and whose range is a set of vectors. R of t is equal to f of t, comma g of t, comma h of t. Okay, this is a vector value function. Okay, this is a function whose domain is a set of real numbers and whose range is a set of vectors. Okay, so the t, the domain here is t, the range, okay, the range is f of t, g of t, and h of t. Okay, so if we want to put this into standard basis form, this would be f of ti plus g of tj plus h of tk. Okay, number one, find the domain of r of t is equal to t cubed natural log of 3 minus t and the square root of t. Okay, f of t is equal to t cubed, g of t is equal to natural log of 3 minus t, and h of t is equal to radical t. Okay, so what are the domains on these? What's the domain for t squared, t cubed? What's the domain of t cubed? Not everybody at once.
All real numbers.
Okay, there you go. All real numbers. Thank you so much. All real numbers. Okay, so the domain is all real numbers. What about the domain on this one? The natural log of 3 minus t. Anybody know what that is? What can natural log not be? Well, it can't be 0 and it can't be negative, right? So this is t less than, right? Less than what? Less than 3? Is that right? Does that make sense? If t is less than 3, then this thing becomes a positive value. What about the other one here? This one is t is greater than or equal to 0, right? Okay, the domain on that one. Okay, so we got our vector valued functions. Okay, so what's the combined domain? What's the combined domain? The combined domain here of r of t is what? What's the domain of r of t? Well, what's the domain of t in these functions? Okay, well, we have all real numbers. That's the least restrictive, right? That's the least restrictive. We have t is less than 3, but t is greater than or equal to 0. So what is this? The domain here is that it has to go from 0 to 3, right? Okay, or we could write it in interval notation as 0 to 3. Okay, limit of a vector function. Limit of a vector function. The limit as t goes to a of r of t is equal to the limit as t goes to a of f of t, comma, limit as t goes to a of g of t, limit h of t, okay, number 2, find the limit t goes to 0 of r of t. Okay, find the limit as t goes to 0 of r of t when okay, r of t is equal to 1 plus t cubed I, okay, plus t e to the negative t j, okay, plus sine of t over t k. You want to know what happens to the limit of this thing as it goes to 0, as t goes to 0, okay, r of t. Well, what's the limit as t goes to 0 here? Well, isn't that just 1 plus 0, which is 1, so this is just I. Okay, what happens as t goes to 0 here?
0.
That's 0 e to the negative 1, that's 0, so that's plus 0j. Okay, and then what's this one? This is sine t over t.
Zero.
That would not exist, so you have to use L'Hopital's rule.
Exactly. Who is that? Who's my smart?
Eastman.
Ismin, very good. You're not even in my class anymore. You're like on it. Okay, so yeah, this thing we're going to use L'Hopital's rule on. Okay, we could also use this the squeeze theorem here to find the limit of this thing. We could squeeze it, right? How can we squeeze this thing? Negative 1 over t. Okay. Right. It's less than or equal to sine of t over t, which is less than or equal to 1 over t. It's kind of interesting. Okay. How do I know that that's true? Because isn't sine between negative 1 and 1? Right? Does that make sense? Isn't the sine between negative 1 and 1? Okay, so
Why would sine be between negative 1 and 1 again?
oh, that's the range, right? I mean, if you think about it. Isn't it bounded? Isn't sine bounded by
Oh yeah, by pi.
negative 1 and 1?
Yeah.
Right? So the limit of this thing is limit of 1 over t as t goes to 0. Okay, as this thing gets smaller and smaller and smaller, what's going to happen? This thing's going to go to negative infinity. This thing's going to go to positive infinity. So that actually doesn't really help me much. What would help is if this thing went to infinity. So when it goes to 0, that doesn't help much. Okay, so squeeze theorem doesn't work. Okay, so yeah, let's go to L'Hopital's rule. So this is cosine t over 1, right? Which is equal to, plug in 0, 1 over 1 is 1. Boom, 1. This goes to 1. Okay, that's kind of cool. Okay. So, yeah. So 1k, which which is just k. So what's the limit of this thing? The limit of the thing is I plus k. Okay, so that's standard basis form. Okay, I plus k. Okay, let's talk about space curves. Space curves. I'm tired. Okay, the set C of all points x, y, z in space where x equals f of t, y equals g of t, and z equals h of t. Okay, is called a space curve. And parametric equations and are parametric equations of C. Okay, the vector R of t is the position vector okay, of the point okay, P of f of t, g of t, h of t, and the tip of such a vector traces out a space curve C. Okay, so just think of a space curve as it's a vector valued function, space curve C. And let's go to something that might help us visualize this thing. Okay. Parametric curves. Okay, so this is a space curve. Okay. You see the vector here. Okay. So this is the parametric form h x of t, y of t, z of t. They just call it x of t, y of z, z of t instead of f of t, g of t, and h of t. It's just a parametric form of a curve, okay, called a space curve. Okay, oops, what the heck just happened? Back. Okay, this particular space curve is called a helix. Okay, and if I let t go from t max of, I don't know, let's do, I don't know, 4 pi. Let's allow this thing to go 2 cycles, 4 pi. So, my keyboard for this. Okay, so 4 pi is 12.6. Backspace. So, 6. Let's see what happens here. Okay, I don't know why it's not tracing. Hello? Trace? Animate? Okay. That gives me the velocity vector. We're not there yet. This is the position vector. Okay, samples, 64 samples. I don't know what the samples is. Okay, T min is 0, T max, yeah, functions. Okay, function A, B, C. Okay, window, what's the window at? Okay, x min is 5, 5, z is 5. Oh, maybe that's the problem, is z is only going to 5. We need z max to go further than 5. We need z max to go, where the heck is my keyboard? Show keyboard. There we go. Okay, so this thing is, I want this to go back, and I want it to go to maybe 15. Back. 15. Okay, does that help at all? No. I don't know. I don't know what the samples is here. Samples 64. I'm not going to screw around too much with this. Okay, 120. 128. Okay, so function B, I don't want function B, function C. Oh, redraw display. Here we go. There we go. Boom. Now we get a nice helix. There we go. Okay, so I'm gonna make this. Let's make this just not t divided by pi. Let's just make this t. See what happens. T, and then now let's redraw this way. There we go. There's my helix. There's my nice helix. Okay. Notice that what are the x values? There are 3 cosine t. What are the y values? 3 sine t. And then what's z? It's just t. And so you can see that vector, this vector is r of t. See that vector there? That's tracing this out. That's r of t. Okay, that's the vector r of t. That's tracing this out. Tells me where the x position is. It always tells me where the y position is, and always tells me where the z position is. Okay, I'll put this link I'll put this address copy. I'll put this in the chat box, just so that you guys have it. Okay. Okay, so enough of that. Enough of playing around with that. Let's go back here. Okay, so that's a space curve. Does that make sense? Is space curve? Okay. So that's the idea behind the space curve. It's a curve in space. Okay, let's look at number 3 here. Okay, number 3. Describe the curve.
Can you scroll back down just a little bit? Sorry.
Describe the curve defined by the vector function r of t is equal to 1 plus t, 2 plus 5t, and negative 1 plus 6t. X equals 1 plus t, y equals 2 plus 5t, and z equals negative 1 plus 6t. Okay, so what is this going to look like? Okay. Okay, well, what does this look like? Let's graph this thing and see what it looks like. Okay, so let's graph this thing and see what it looks like. Okay, so this thing is going to be 1 plus t, It's not 1 equals, 1 plus t. Okay, y is going to be 2 plus 5t. And z is going to be negative 1 plus 6t. Okay, and then I'm going to redraw my display. Like, where did it go? Okay, I don't know where it went. Let me think about this. Okay, so make sure we put in our functions correctly. 1 plus t, 2 plus 5t, 1 plus 6t. Okay, when t is 0, this should go through the point 1, 2, 1. Right, 1, 2. Does this graph it for me or no? Okay. So 1, 2, 1. Well, where's the point 1, 2, 1? The point 1, 2, 1, 1, 2, 1 should be like right here. Okay, it's 1. Oh, can I rotate this at all? What the heck? Let me stop sharing for a second. I'm having a hard time rotating. Whatever. Okay, let's do it. Let's do it old school. Okay, no school like the old school. Let's see what this thing's gonna look like. Let's plot some points here. Okay, when t is equal to 0, and this becomes 1, 2, negative 1. Okay, when t is equal to 1, this thing becomes 2, 7, and 5. Okay, when t is equal to 3, this thing becomes. Now the idea here is this. Think of this as 1 plus 1t, where this is a line, right? Think of this as the x-intercept, and then it has a slope. Okay, an x-intercept. When t is equal to 0, this is okay, and then the slope is 1 here. Okay, every time t goes up, we go up 1. Okay, so this is going to be 3, right? Every time this is t is equal to 2. Sorry. Okay, 1, 2, 3. Every time I increase by t, this is going to go up by 5. That's 12. Every time I increase t, this becomes goes up by 6. So this is 11. So what this is this is the equation. We think about it, right? Like we're going out. We're going to start when t is equal to 0. We're starting at 1, 2, and then negative 1. Well, negative 1 is down here, so we're starting here. And where are we going from this point in space? Well, in the x direction, we're always going to go up 1. We're always going to go up 1 in the x direction. We're always going to go up 5 in the y direction. Yeah. Oh, that's the z direction, sorry. Five in the other direction. Okay, so 5. Okay, so we're going to go out 1. We're going to go up 5 in the y direction. Okay, and then we're going to go up 6 in the z direction, right? So z is always going up 6. Right? And we would always do the same thing. We would always, from point to point, we would always do the same thing. And so what are we getting? We're getting the equation of a line. Okay, which should make sense because wasn't, you know, this the parametric form of a line? And that is just a simple space curve. Okay, so that's just a simple space curve. It will create a line. Why? Because we're always going up over, we're always changing. Our rate of change is always the same for every point. Okay. Okay. Number 4, sketch this curve. Sketch the space curve. R of t is equal to cosine ti plus sine tj plus tk. Okay. So let's look at some values of t here. Okay, t cosine t, that's my x value. Sine t, that's my y value. And then t, which is just my t value, that's my z value, right? So when t is 0, what's cosine? Well, cosine is 1. What's the sine? 0. What's t? 0. So this is going to be at 0.100. Okay, what about pi over 2? Pi over 2, this thing's going to be 0. This is 1, and this is pi over 2. So this is going to be 0, 1, pi over 2. Okay. And so we can see that the x, y's, if we didn't have the z, this would just create a circle, right? It would just look like this. It would create a circle. Okay, but what's happening is we're increasing in the z's as well. So we're going around this unit circle. We'll say that the unit circle is here, 1s. We're going around this unit circle, but what are we doing? We're increasing. And so we get that nice little helix. Does that make sense? We're increasing our z values as we go around the unit circle. Which is exactly what I had drawn here, which just was a little bit different because it had 3 in front of it, just to make it a little bit nicer of a graph. But it's the same graph. Let's go back to the drawing here. Okay, that's the default. If we get rid of the 3, though, okay, this is the one that we're working with here. Okay. It's just going to be a little thinner. And again, I wish I could figure out how to manipulate this thing. But there's got to be a way. Oh, wait, what the heck? How did I do that? How the heck did I do that? I used 2 fingers? 2 fingers? I can zoom in, zoom out. I don't know. I'm used to my app on the iPhone. This thing is so much nicer on the iPhone. So it's like, I could really mess with it and it would be really nice. So there is an app for this on the iPhone. I don't know if it's available anymore. But on my iPhone, I do have the app. Or an app. Let's see. It's called 3D Grapher. 3D Grapher here. Okay, so nope, that's not it. I want the parametric one. 3D calculator. Is that it? Nope. That's not it. I'll have to see which one it is, but there is an app on the calculator for this. A graph does space curves. It graphs space curves. Okay. So this thing is sine. Come on. Oh. Cosine, sine, and then this is just t, lowercase t. Enter. Okay, let's redraw this thing. Okay, and there we go. This is just one cycle because it's going from 0 to 2 pi. They're just showing one cycle of it. Okay. And again, it would be nice to orient this positively, but you get the idea. I don't know what's going on here. Maybe I use my mouse. If I use my mouse, maybe that's better. I'm trying to do the touch screen. Let's use the mouse. Let's see what we can do. Oh, there we go. Perfect. Yeah, it just wants the mouse. So there we go. Boom. Starts there, and it spirals up. Okay. Ooh, just like a slide. Okay. So let me do a new share on this. Okay, and there we go. This is what I'm trying to show you. Okay. So cosine t, sine t, and t. Okay, so this would be just the unit circle in 2 dimensions, but because we add that third dimension, it's a helix. It spirals up. Okay, so this is called a helix. Okay. Let's find the line segment here. Find a vector equation of the line segment through point 1, 3, negative 2, and Q, 2, negative 1, 3. Two, negative 1, 3. Okay, so R of t is equal to 1 minus t times R naught plus t R1. Remember, that's our line segment. That's our line segment equation. Okay, so what's R naught? What's R naught in this case? Well, we're just going to let R naught be the vector from the origin to P. R naught is going to be equal to 1, 3, negative 2. Okay, what's R1? R1, I'm just going to say, is after t is equal to 1, when t is equal to 1, we get R naught, R1. Right? Does that make sense? When t is equal to 1? Because what's 1 minus 1 here? If I plug in 1 here, what's 1 minus 1? That's 0. That cancels that out. And if I plug a 1 in there, isn't R of t just equal to R1? So this is when t is equal to 0. We get R naught. When t is equal to 1, we get R1. And so what's R1? Well, that's just going to be my endpoint. This is my beginning. At t equals 0, we have P. At t equals 1, we have Q. So initial point, terminal point. Initial point is P, terminal point is Q. So this is just the vector 2, negative 1, 3. Okay. So let's just plug this in, see what we got here. Okay, so R of t, this is the space curve, but the space curve is just, it's a space curve, but it's just a segment of a piece of line in three space. Okay, just some sort of piece of line in 3 space. Okay, so what's 1 minus t times R naught? It's 1, 3, negative 2, plus RT times R1, 2, negative 1, 3. Okay. So now what I'm going to do is distribute. I'm going to distribute. This becomes 1 times 1 minus t. You have a question? No? Okay. This is going to be 3 times 1 minus t. This is going to be negative 2 times 1 minus t. Okay, plus 2t minus t 3t. Okay, so now I want to add component to component. Okay, so this is going to be 2t times 1. Well, maybe I'll just distribute. Okay, this is 1 minus t. This is 3 minus 3t. And this is negative 2 plus 2t. Now I want to add component to component. Negative t. Okay, what is this? Come on. Come back to me. Of course. I didn't go. What the heck? Go away. Technical difficulties. Okay, so this is 2t. This is negative t, and this is 3t. Okay, so now let's add these together. What is 1 minus t plus 2t? Wasn't that 1 plus t? Right? What is 3 minus 3t minus t? Wasn't that 3 minus 4t? And what is negative 2 plus 2t plus negative t, or sorry, plus 3t? Wasn't that negative 2 plus 5t? Yeah. So r of t is equal to this thing. Okay, so what's our line segment here? What's our line segment? Well, it's this piece of line here. Oops. Stop, go away. There we go. Okay, so it's a piece of line segment. This whole thing makes a line. 3 minus 4t, z is equal to negative 2 plus 5t. But in order to get the piece of line that I'm interested in, that has an initial point of P and a terminal point of Q, okay, that starts at P and ends Q, I can only let T go from 0 to 1. Okay. Does that make sense? Okay, so this is my line segment. Okay, I could write that in standard basis form too if I wanted to. R of t is equal to 1 plus t, I, okay, plus 3 minus 4tj, plus negative 2, that's a negative, right? Yeah, negative 2 plus 5t, k.
I just have a quick question. For the equation that you were showing at the beginning, the r of t equals 1 minus t times r sub 0 plus t r sub 1. Does that represent just the vector equation in general, or just of a line segment, or what does that represent again?
It's the equation of a line segment.
Okay, thank you.
It's the equation of a line segment in R3. Okay, so that's your equation of a line segment in R3, and I'm just simplifying it and saying, hey, this can get simplified to this parametric form or this standard basis form. But again, I have to make sure that I know that it goes from 0 to 1. Okay, otherwise it's not a line segment. It's the whole line.
And then can you also go over how you got 0 to 1?
How did I go 0 to 1? Yeah, sure. Okay, so let's think about this for a second, right? So yeah, that's a great question. Who asked that question?
Jose?
Jose. Thank you, Jose. Yeah, that is actually a really good question. So what did we have? We had 1, 3, negative 2, right? And then what was Q?
2, negative 1, 3.
2, negative 1, and 3?
Yeah.
So if t is equal to 0, then I want 1, 3, negative 2. If t is equal to 1, then I want 2, negative 1, 3. Okay, so how can I go from 1 to 2? How do I go from 1 to 2?
By adding 1.
Adding 1. I could say this is 1 plus 2. Right? How do I go from 3 to negative 1?
3
How do I go
minus
from
4.
3 to negative 1? What do I do?
3 minus 4.
Yeah, 3 minus 4. So I'm going to subtract 4, right? So we would start at 3 and we would go 4t, right? And then how do I go from negative 2 to 3?
You add 5.
Yeah, add 5. Right, so that if I want the line segment between P and Q, well, at t equals 0, what's my point?
1, 3, negative 2.
At t equals 1, what's my point?
It's point Q. 2, negative 1, 3.
Negative 1, 3.
Okay.
Does that make sense?
Yeah, that makes sense. Thank you.
Yeah, you're welcome. Okay, and then we just want everything in between, right? So we just let t go from 0 to 1. Yeah. Okay, number 6. Number 6, find a vector function that represents the intersection of the cylinder x squared plus y squared equals 1 and the plane y plus z equals 2. Find a vector function that represents the intersection of this. Okay, so how's this going to work? Well, we have a cylinder, right? We have a cylinder. Okay, let's look at the cylinder here. Let's just look at the cylinder. I'm not going to put it in. I'm just going to look at the cylinder. Okay, so let's draw a cylinder real quick. Okay, here's my cylinder. Does everybody get that this is a cylinder? That's a cylinder. Make sense? So far, so good. Okay, now the cylinder has no top or bottom on it, right? Remember that? Remember, it's just it goes this goes up forever. And this goes down forever. Does that make sense? From last time? Okay, so there's my cylinder. So now what I'm going to do is I'm going to slice this up. I'm going to have a plane. I'm going to have a plane that goes through this. Okay. And so what does this create when this slices through?
A trace.
Right? So think of this as a see-through. Slices through, and what I get is an ellipse. Does that make sense? Maybe I didn't draw it too well, but this should be an ellipse. Does that make sense?
Yes.
Slicing it through. Okay, it looks like a circle. I apologize for that, but if I made my plane a little bit maybe steeper, it would be an ellipse. So what is the ellipse? What is the ellipse? Well, we have this cylinder x squared plus y squared equals 1. How could I parametrize this? Anybody know how I could parametrize this? Make it a parametric form? Anybody know what the parametric form of a circle is?
Would you use sine squared of t plus cosine squared of t, or
Yes,
no? Oh yeah, okay.
absolutely. So you would say that x is equal to cosine t and y is equal to sine t, right? Because isn't cosine squared plus sine squared equal to 1? Right? Kind of like turning it into polar coordinates, right? We're parametrizing this. Okay. Okay, and then how would I get my y value? How would I get my y value, or my z value? Well, isn't z equal to 2 minus y? And so what's z? Z is or what's y? Well, we already said that y was sine t, so isn't this 2 minus sine t? Right? 2 minus sine t. So we have x is equal to cosine t, y is equal to sine t, and z is equal to 2 minus sine t. Okay. Okay, so this is an ellipse in the plane. Okay, so let's bring this all together. What's r of t? Well, r of t would be cosine ti plus sine tj, right? So this is a space curve, plus 2 minus sine t k, right? So this is an ellipse. Okay, now how could I figure out what the heck's going on here? Well, if I wanted to graph this, t, okay, I would get x, y, and z, right? X, y, and z. Okay, so let's plug in 0 for t. What's x going to be? Well, that's 1. This is 0, and then this is 2, right? 2, because the sign of 0 is 0, so 2 minus 0 is 0, right? Okay. What about pi over 2? This would be 0, 1, and 2 minus 1, which is 1. So this becomes 1, 0, 2. This becomes 0, 1, 1. Okay. Okay, what about pi? At pi, where are we at? At pi, where are we at? Well,
You'd have -1, 0, and 2.
Yeah, -1, 0, 2. Very good. Okay, what about 3 pi over 2? 0, -1, and 3, right? Makes sense. And then what about 2 pi? Wasn't it the same as 0? Aren't we back to where we started? Right, so what would this look like in 3 space? What would this look like in 3 space? I did it again, same thing. It's really hard to draw through the center. Okay, in 3 space, what would this look like? Okay, we're at 1, 0, 2, 1, 0, 2, 1, 0, 2. So we're over 1 in the x direction. We're up we're out 0 in the y direction, then we're up 2 in the z direction. So we're right here. Does that make sense? 0, 1, 2. What about 0, 1, 1? I'm sorry, sorry. Yeah, 0, 1, 1. So we're out 0 in the x direction. We're up 1 in the y direction. I'm sorry, we're out 1 in the y direction. We're up 1 in the z direction. So that's there. I'm going to get rid of this line here. I don't need it for the graph. It's going to mess up the perspective. Okay, what about the next one here? What, negative 1, 0, 0. Well, that one's kind of easy. Negative 1, 0, 0 at pi. Okay, so negative 1, 0, 0. So negative 1, 0, 0. That's x negative 1.
Oh, I thought that point was negative 1, 0, 2.
Oh yeah, it's negative 2. Thank you, thank you, thank you. Yes, it's negative 1, 0, 2. Okay, so negative 1, 0, 2 is negative 1 in the x direction. So that's there, and then 0 in the y direction, then an up 2. Oh, okay. It's kind of the mirror image here. So it's looking like we're doing this. That's kind of cool. Okay, and then what's the next one here? It's 0, negative 1, 3. So 0 in the x direction, negative 1 in the y direction, 3 in the z direction. So up here. So let's finish this curve like so. And then we can see that this is the slice inside the cylinder, right? Does that make sense? It's a slice inside the cylinder here, with this plane slicing.
So is a slice in an angle?
Yeah, it's slicing.
That makes sense.
Exactly.
Okay.
And it creates an ellipse. So, yeah. Okay. 13.2. Okay, derivatives and integrals of vector functions. Okay, derivatives and integrals of vector functions. If r of t, I'm sorry, I need to go get a drink. This is a water checkpoint, so I'll be back in 30 seconds. Okay, my mouth is getting super dry. Okay, I'm back. I got my chocolate milk here. It's good stuff. Okay, might help me. help me get through the next hour here. Woohoo. Okay, derivatives and integrals. Let's look at our vector valued function here. Okay, r of t. Okay, if r of t is a vector, then dr dt, the derivative of this thing, equals r prime of t, okay, is equal to the limit as h goes to 0, okay, definition of derivative here, h goes to 0 of r of t plus h minus r of t all over h. Okay, and this is called the tangent vector. This is the tangent vector. Okay. So, okay, we also have, well, let's look at our helix, okay? Let's look at helix the cat here. Okay, I'm sorry, helix the space curve. Okay, so let's look at our helix. Our helix looks like this. Right? Here's our helix. And so at any given value here, we have r of t, that's my position vector. R of t is the position vector. But r prime of t is called the tangent vector. Okay, and so it's tangential, okay, to this. Think of r of t as your velocity, v of t. Right? Where's your velocity headed? It's v of t. R double prime, which we'll get to later, okay, think of it as a of t, that's your acceleration. Okay, so as I travel around this thing, okay, if we look at a circle, right, what's r of t? Well, it's the position vector, right? What's the velocity vector? Well, it's always tangential to the circle. Okay, in this case, it's orthogonal to, you know, r prime of t and r of t are orthogonal to each other. What would be a of t? A of t is actually this guy here, the acceleration. Right? The acceleration this is called centripetal acceleration, and it always points in. So the r of t points out, the v of t points up, okay, or is tangential to the position, and the acceleration is parallel to is orthogonal. So we've got orthogonal, 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 right? So it's kind of like we've got two left turns here. You got left, left, right, left. So it reminds me of this saying here: two wrongs don't make a right, but three lefts do. Okay, so think about that for a little while. Okay, what does it mean? Three lefts make a right. Start here, you go left again, right? Okay, so left turn, and then left turn. Okay, what did you do? You made a right turn. Went the other direction. So two wrongs don't make a right, but three lefts do. Okay, anyway, I digress, but this is the v of t, or the tangent vector. Okay. Okay, the unit tangent vector. The unit tangent vector. Okay, called t of t, is r prime of t over the magnitude of r prime of t. That's the unit tangent vector. So we're saying that if we have this helix guy here, okay, and we have a tangent vector, say here, okay, we want one unit, we could make this 1 unit by just dividing by the magnitude. Okay, we would unitize that. We would make it a standard vector length of 1. Okay, so T of T would have a vector length of 1. Okay, so the magnitude of T of T is equal to 1. Oops, what the heck did I do here? Okay, so the magnitude of T of T is going to be equal to 1 because it's a unit vector. It's of length 1. Okay, number 1. Okay, find the derivative and unit tangent vector. Again, I might go to Desmos on this one, or not Desmos, to my parametric curve grapher, and here I can show. It says, what do you want to display? I want to display on this guy more settings. I want to display the velocity vector. So I can display the velocity vector here. Okay, and you see, look at that. There's a velocity vector. Right? So the position vector is r of t. The velocity vector is r prime of t. Okay, and if that was a unit length, then that would just be the unit tangent vector. Does this make sense? I mean, the picture is worth 1,000 words. Hopefully this makes sense. Okay.
Can you repeat what you just said one more time?
What I'm saying is that the position vector, r of t, originates from the origin. And then the tangent vector is the kind of like the velocity vector. Okay, and it's tangential to the space curve. Now, why is it tangential to the space curve? Because it's a derivative. And aren't derivatives tangent lines? Does that make sense?
Yeah.
Yeah, the derivative is tangential to the curve at a point. Right? So again, I hope the animation here helps you visualize this. Okay? So get this idea here. Okay, maybe if I get rid of this thing, it'll be a little bit better. Okay. Does that help? Whoosh. Okay, it's going in the direction of motion, that tangent vector. So we think of it as the velocity vector. Okay, but I'm getting ahead of myself. Okay. But a unit tangent vector is of length 1. The magnitude of that is 1 because we're creating it as a unit vector. Okay, find the derivative. Okay, find the derivative and unit tangent vector for t equals 0 of r of t equals 1 plus t okay, 1 plus t cubed okay, I, plus t e to the negative t, j, plus sine 2tk. Okay, so we want to find the derivative and unit tangent vector of this. Okay, well, how do we find r prime of t? Well, if r of t, if r of t of s is f of t I plus g of t j plus h of t k, what do you think we're going to do to find r prime of t?
Take the derivative of x, y, and z.
Exactly. Right? That makes sense? Okay, so let's just find the derivative of this, r prime of t. This is going to be 3t squared. This is going to be the product rule, t e to the negative t. So the derivative of t is 1. So this is e to the negative t plus t, okay, times e to the derivative of e to the negative t is negative e to the negative t. Right? And then plus sine 2t, that's a chain rule. That's just going to be 2 cosine 2t. I could do this as ij's and k's as well. This is I plus, okay, this thing j plus this thing k, right? So let's clean that up. Let's simplify that. R prime of t is equal to just 3t squared I plus, I'm going to factor out an e negative t, so this becomes 1 minus t j plus 2 cosine 2tk, and that's the derivative. Okay, so how do we find the unit tangent vector here? Okay, so what's the magnitude of this thing going to be?
0.
No. How do we find the magnitude of r prime?
You would square each piece, like you would square 3t squared and then plus blah, 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 and you would just square everything and then take the square root of it all.
Exactly. Okay, so we would say that this thing is going to be, okay, the square root, right? So let's find the magnitude of r prime of t is the square root of 3t squared squared plus e to the negative t times 1 minus t squared plus 2 cosine 2t squared, right? Okay, so this is equal to 9t to the fourth plus e to the negative 2t times 1 minus t squared plus 4 cosine squared 2t. But what we're really interested in is what's t of 0? What's the unit tangent vector evaluated at 0? That's r prime of 0 over the magnitude r prime of 0. What's r of 0 or r prime of 0? We'll plug in 0 here. We get 0, 1, j, right? 1j. Okay. We get 1j. We get 0, 0i plus 1j. And then what's cosine? Cosine of 0 is 1. 1 times 2 is 2. So plus 2k. All over the magnitude here at 0. We'll plug in 0 for this magnitude here. That's going to be 9 times 0, which is 0. This goes to 0. This thing goes to 1. That goes to 1. This thing goes to 1. So that's just 1. This thing is going to go to 1. And 1 times 4 is 4. 1 plus 4 is 5, so this is just radical 5. So this equals, okay, the unit tangent vector at 0, evaluated 0, is going to be equal to 1 over radical 5j plus 2 over radical 5k. That's the unit tangent vector evaluated at 0. Make sense? Okay, number 2.
Can you scroll down a bit, please? Thank you.
Okay, number 2. Yeah, what's up? I need another drink of my chocolate milk. Okay. I had carrot cake for dinner last night. I had powdered donuts for breakfast. And I've now had chocolate milk for lunch. I'm going to die soon. I think tonight I need to have some sort of vegetable. Yeah. So I digress. So anyway, I'll try to do that. Eat something healthy, because I haven't in the last 24 hours. Okay. 4, when I get stressed out, my diet is the first thing to go. Is anybody else like that? You're just like, I'm stressed and I'm going to eat like crap. So, I don't know. Maybe it's just me. For the curve r of t is equal to radical ti plus 2 minus tj. Okay, so this is an R2. Okay, find r prime of t and sketch r1 and r prime of 1. Okay, find r prime of t and sketch both r of 1 and r prime of 1. Okay. Let's see what happens here. Okay, so what's r prime of t? Well, that's 1 over 2 radical t, right? I. Okay, minus j. Is that right? Does that make sense? Okay. Okay, so what's r? Well, first, what's r of 1? What's r of 1? R of 1, plug 1 in here. It's I plus 2j. Okay. What's r prime of 1? It's 1/2 I minus j. Right? Is it 2? No, it's 1. I'm sorry. This is 1. Because it's 2 minus 1. Yeah. Okay. Okay. So what is this? Let's look at this as a vector. This is the vector 1, comma 1. And this is the vector 1/2, negative 1/2. Okay. So now we want to graph this thing. See what the heck does this thing look like? Okay, what is this going to look like? Okay, we have this curve, r of t is equal to the square root of t plus 2 minus t. So that's I in the I direction. This is the x direction. This is the j direction. Interesting. Okay, so what at r when at r of 1, when r is 1, what do we get? Well, we're going to be at 1, 1, right? 1, 1. Does that make sense? 1, 1.
I just have a quick question about the r prime of 1. it says that it's 1/2 comma negative a half. But wouldn't it be 1/2 comma negative 1 since it's just minus j?
Oh,
Or
yeah, I messed up. I'm sorry.
oh, okay.
Yeah, thank you so much. Okay, it's, yeah, 1/2 minus 1. I wrote it correctly over here, but for whatever reason, I duplicated my thought. Okay, perfect. Okay, so this is, right, this is r of 1. Does that make sense? This is r of 1. Okay, when t is 1, I'm at 1, 1. Make sense? Okay, what about r prime of 1/2 negative 1? Well, that exists when r is equal to 1, right? The tail of this, or sorry, the tail of this thing is going to start, okay, at 1, 1. It's going to start at 1, 1. Why is the tail going to start at 1, 1? Because it's tangential to the curve at this point. Okay, it's tangential to the curve. If I started it at 0, it would look like this. We're going to go negative 1/2 in the x direction. Okay, negative 1 in the y direction. So let's do a negative 1 here. And it would look like this, right? Half, and we go look like that, right? So that, but that's not where it is. That's not the location of this vector. The location of this vector really is, okay, I'm going to go down 1 over 1/2 from this point. This is my tangential vector. This is r prime of 1. Does that make sense? Hopefully that makes sense. This is 1, this is 2. Okay, so what does this curve really look like? I mean, what does this curve really look like? This is, I mean, in a way I could graph this curve. Okay, how could I graph this curve? I could say that x is equal to radical t, y is equal to 2 minus t, right? So what is t equal to? Isn't that equal to x squared? So wouldn't this be y is equal to 2 minus x squared? What is that? That's a parabola starting at 2, and it's going down. Right? If we turn it back to rectangular form instead of parametric form, isn't that a parabola? And this r of t is the vector valued function in 2 space that will give me all the points on this parabola. And then what's the tangential vector here? The tangential vector, the tangent vector at 1, 1 when t is equal to 1, right? When t is equal to 1, where am I at? Well, when t is equal to 0, where am I at? When x is equal to 0, where am I at? Don't I start at 2? 0, 2. Let's think of x as t, right? X is t. Okay, because, you know, especially for 0 and 1, because what's 0 squared? Isn't that 0? Isn't the square root of 0, like if t is equal to 0, then what's x? X is 0, right? When t is 0. What's x when t is 1? X is 1 when t is 1, right? So anyway, I think I've beat that. It's a dead horse at this point. So does that make sense? This is r prime of 1. Okay, let's move on. What time we got? 5:14. We got a half hour. Okay. Half hour, and then I got a week to recuperate, which is good. It's all good in the hood. Okay, let's do this. Let's push through. Power through, baby. Power through. Okay, first exam is on the what? 16th? Keep that in mind. It's coming up here. Okay. 2 weeks? Yeah, 16th. First exam. Okay, number 3. Find the parametric equations for the tangent line to the helix x equals 2 cosine of t, y equals sine of t, z equals t. At the point 0, 1, and pi over 2. Okay, so what's r of t? R of t is this guy here. It's 2 cosine t, sine t, and t. Right? So we want to find the parametric equations for the tangent line to the helix. This is now the tangent line. Okay, so to this helix at this point when t is equal to something. I don't know what's t going to be equal to. We know that x is equal to 0. So we want to know what value of t is going to create 0 here. Okay, so so what's z? Isn't z equal to t? So what's the z value here? What's z? Isn't
Pi
z
over 2.
Yeah, pi over 2. So isn't t equal to pi over 2? Right? So t is equal to pi over 2. Oh, okay. So how do we find a tangent line? Well,
Take the derivative.
yeah, let's find the derivative. Right? Let's find the derivative. So we're going to say that r prime of t is equal to what? R prime of t is going to be negative 2 sine t, cosine t, and 1. So the derivative, it's kind of interesting. The derivative has nothing to do with z. The derivative has nothing to do with z. Oh, that's kind of cool. Okay. Remember think of the derivative as the velocity here, right? What type of curve is this? What type of curve is this that we're dealing with? Anybody know?
Helix?
Yeah, it's the helix, exactly. And so does it make sense that the velocity doesn't change with respect to z? Why? Because really all you're doing is going around in a circle. In this case, we're not going around in a circle. What are we going around in? Aren't we going around in an ellipse? Right? Isn't the x direction twice as big as the y direction? So aren't we going around in an ellipse? But as we go up the ellipse, the velocity vector doesn't really change based on z. Why? Because we just keep tracing that elliptical pattern. Does that make sense? So the velocity does not change based on how high we are. It only changes on where we are in that elliptical orbit. Right? Okay. Okay, so what's r prime? Well, first of all, what's r prime of pi over 2? What's r prime of pi over 2? So this is going to be the slope of the tangent line. Okay, you can think of it as slope. Okay, although slope is just changing y over changing x, but this is actually changing y or changing x, changing y, and changing z all at the same time. It's the change in x, the change in y, and the change in z. So it's really not slope, because it's not a proportion. We're just saying every time we're changing in the x direction a certain amount, we're changing in the y direction a certain amount, and then we're changing in the z direction a certain amount. Oh, okay. Okay, so what is this? Plug this in. Isn't the sine of pi over 2, what is that, 1? So wouldn't that be -2, 0, and 1? Does that make sense? So that's that. Okay. So how do I find the equation of a line? Okay, equation of a line. Remember, this is where is this occurring? Isn't this occurring at the point 0, 1, and pi over 2? So we have a point and we have a vector. How did we get the equation of a line when we had a point and a vector?
You subtract it?
Wasn't the equation r equals r naught plus vt? You remember that? Does that make sense?
Yes.
Yeah, so this is the equation of a line, okay, with a point and a vector. I'm not going to call it r because we've already used r. I'm going to call it s. Okay, because we don't want r. R has already been used for the space curve. We're just going to call this s. This is the equation of the tangent line, okay, with point 0, 1, pi over 2 plus vector. This is my vector function, okay, -2, 0, and 1 times t. Okay, so s is equal to, okay, this is going to be -2t. This is going to be 1, and this is going to be pi over 2 plus t. So x is equal to, if I put this in parametric form, x is equal to -2t, y is equal to 1, and z is equal to pi over 2 plus t. That is the equation of the line. This is the equation of the tangent line. In R3. Okay, notice that the equation of the line is different. Okay, it's different. Okay. Okay, number 4. Okay, show that if the magnitude of r of t is equal to a constant, then r prime of t is orthogonal to r of t for all t. Okay, like it's orthogonal. Okay, interesting. Okay, so let's think about this for a second. Okay, what is r prime of t, or how would I rewrite r of t, the magnitude of r of t? Anybody remember what the magnitude of r of t was? I could rewrite this in terms of x, y, and z, right? Does that make sense?
Square root x squared plus y squared plus b squared.
Yeah, exactly. Okay, you could think of this as x of t squared, y of t squared, z of t squared if you really wanted to. Okay, but we're saying that the magnitude of this thing had to be equal to a constant. So these can't be functions. Does that make sense? If x of t, if x of t was anything other than just x, or y of t was anything other than just y, or z of t was anything other than just z, then I would never get a number out, just one number. It would be a function of t. So that's why we don't do x of t here, y of t, or z of t. Does that make sense? Because you wouldn't get a constant. The only way you're going to get a constant is to have x, y, and z be constants themselves. Does that make sense?
Yeah.
Okay, sounds good. And so what I'm going to do is I'm going to square both sides. I'm going to square both sides here. I'm going to say that x squared plus y squared plus z squared is equal to c squared. Okay. And I'm going to do something a little tricky. Okay, I'm going to do a little tricky. It's going to be a little different. I'm going to go x times x. Well, let's do x times x plus y times y plus z times z is equal to c squared. Why do you think I did that? Any ideas?
Maybe so you can somehow separate the variables, like instead of dividing everything by x squared by just x or something like that.
Sort of. Let's think of vectors. Let's think of vectors. Let's think of the vector x, y, z. How would I get this? In terms of
Substituting the values in, or the equation.
From the two separate points?
no? I want to turn a vector into a scalar. I want to turn a vector into, how do we turn vectors into scalars?
Dot product.
You cross.
How you heard it?
Dot product.
Dot product. Thank you, Armando. Dot product. So isn't this guy just dotted with himself? Does that make sense?
Yeah, that makes sense.
Isn't this just x, y, z dotted with x, y, z? Equal to c squared. Okay, what is x, y, and z though? What is x, y, and z? Isn't that just r of t? Isn't r of t equal to x, y, z? Does that make sense? So wouldn't this just be r dot r is equal to c squared? Or we could say r of t, right? R of t. So r of t, okay, dotted with r of t, isn't that equal to c squared? Does that make sense?
Yeah.
Now what we're going to do is we're going to take the derivative of both sides. d dt, d dt. What's the derivative of a constant?
0.
Yeah, derivative of a constant is 0. So this becomes d dt of r dot r is equal to 0. Oh, okay. What's the derivative of r dot r? Well, think of this as the product rule. Okay, this would be r derivative of the first dotted with the second plus the derivative of the second dotted with the first. Well, both they're the same thing here, so it's the first dotted with the derivative of the second, right, is equal to 0. Okay, so the dot product, that's kind of a rule of derivatives here. d dt of r dot r Okay, or we could say a dot or v dot u or anything like that. D dt of v dot u is equal to v prime u dotted with u prime v, right? So either way. Okay, that's a rule of the property of derivatives of vectors. Okay. And so don't we end up with two identical things? Isn't this 2 times r dot r prime? That makes sense? We end up with 2 of those is equal to 0. Divide by 2. So r dot r prime is equal to 0. And what do we know when we get the dot product of 2 items that they're and it equals 0?
Doesn't that prove that it's orthogonal?
Exactly. So we know that r and r prime are orthogonal. So it's a nice little proof. Okay, what does this prove? This proves also that if we get the magnitude of the magnitude equal to c of r of t, then we get x squared plus y squared plus z squared equals c squared. I'm going to replace the c with r. What is this? What's this equation here? What's that equation of?
Is that maybe the equation of the sphere in 3 dimensions?
Absolutely. This is the equation of a sphere with radius r. And what does this tell me about any tangential curve to a sphere? What does this tell me about any tangent to a sphere? All tangents to a sphere are what?
Are equal to r squared.
They're all orthogonal.
They're all orthogonal.
They're all 90-degree angles. Does that make sense? All tangents to a sphere are perpendicular to the radius. Okay, they're all perpendicular to the radius. Okay, let's look at integration for a second. Okay, integration of space curves. Okay, if r of t is equal to f of t I plus g of t j plus h of t k, then the integral from a to b of r of t dt is equal to the integral from a to b of f of t dti plus the integral from a to b of g of t dti plus the integral from a to b of h of t dt, or sorry, this is j, I'm sorry, j, and then this is k.
Sorry, I think somebody in the chat asked if you could scroll up a bit or scroll down.
Okay. Are you good? It's just, I mean, you don't even really need to know that. It's just kind of a bonus. Okay, so we just integrate the pieces individually. Okay, so also, if the integral from a to b of r of t, this is fundamental theorem of calculus, is r of b minus r of a. Okay. Okay, where r is the antiderivative where capital R is the antiderivative vector of R. Okay, think fundamental theorem of calculus on that one. Okay, so number 5. If R of t is equal to cosine ti plus sine tj, again, this goes back to our helix, plus sine tj plus 2tk, there's our helix, our friendly helix. Okay, find R, the integral of R of t dt, and we'll put limits on this thing, 0 to pi over 2 R of t dt. Okay. So let's integrate this thing individually. So the integral of R of t dt is going to be equal to what? Okay, it's going to be equal to cosine, the integral of cosine t. What's the integral of cosine t? It's sine t plus c. Okay, some constant, right? Sine t plus c. I'll call that constant 1, or we can even say constant x, cx. Right? It's the constant that goes to our x coordinate. Maybe I'll do c1. Okay. I. Plus, what's the integral of sine? Isn't that negative cosine? Negative cosine of t plus c2 j. Okay, plus the integral of 2t, that's t squared, plus c3 k. Make sense? Okay, well, I could combine all these constants, okay, into just one constant, where it's where c is the vector constant of integration. I could say that this is I could distribute the I, the j, and the k, and I could say this is sine t of I plus or minus cosine t j plus t squared k okay, plus what? Plus c1 I plus c2 j plus c3 k. And I'm just going to call this vector c. Does that make sense? This is a vector. That's just a constant vector. Okay? That's my constant vector. So I can really just erase this and just put c. Knowing that capital C is a vector, not a scalar. This guy is a vector. Okay. So now what do we want to do? We want to evaluate this thing. We took the integral. Now we want to evaluate it from 0 to pi over 2, right? R of t dt is going to be this thing sine ti minus cosine tj plus t squared k. We don't need the constant because it's a definite integral. And so we're going to go from 0 to pi over 2. So sine of pi over 2 I minus cosine of pi over 2 j plus pi over 2 squared k. Okay, so what's the sine of pi over 2?
1.
1, okay. Okay, so sine of pi over 2 is 1, is that right? So 1i minus, what's the cosine of pi over 2? Isn't that 0? 0j plus pi over 2 squared, right? Okay, now I want to subtract that from what? The same thing, but we were going to plug in 0. Okay, minus the sine of 0 minus cosine 0 plus 0 k, right? So this is ijk. So sine of 0 I minus cosine 0 j minus minus 0 squared k. Okay, what's the sine of 0? Isn't that 0? Isn't that 0i? What's the cosine of 0? Minus, that's 0i, not j. What's the cosine of 0? Isn't that minus 1j? And then this is 0k. 0k. Okay. Distribute the negative sign. And what do we get? We get 1i, which is I. We get plus 1j, which is j. And we get, that's 0, that's 0, that's 0. Okay, and then we get plus pi squared over 4k. That's it. That's the integral. That's it. That's all I got for you guys. So I'll see you next Wednesday. Okay, no office hours today. I'm sorry. I'm just not feeling up to it.
Thank you, Professor.
Welcome.
Thanks.